Modern swept spectrum analyzers are sometimes referred to as narrowband receivers. This is primarily because they provide an adjustable resolution bandwidth filter, also known as the RBW setting. The signal selection progress of the resolution bandwidth filter in a super heterodyne swept analyzer is as below. First, tune the input signal to an intermediate frequency by the local oscillator. Then filter the signal in a specified bandwidth to get the corresponding amplitude. As the intermediate frequency, or IF, is swept through the filter, the screen will display the filter's shape. Spectrum analyzers commonly use a Gaussian RBW bandpass filter to achieve short response time. In this case, there are two key specifications for the instrument: the resolution bandwidth and the selectivity of the filter. RBW is the 3 dB bandwidth that indicates the spectrum analyzer's ability to distinguish two frequencies that are near one another, both having the same amplitude. Selectivity is the ratio of the 60 dB bandwidth to the 3 dB bandwidth measurement of an input signal. It indicates the spectrum analyzer's ability to distinguish frequencies with different amplitudes. The selectivity of the DSA-815 is lower than 5 to 1 and is much better than an analog intermediate frequency filter, typically achieving 10 to 1 or 14 to 1 ratio. Now let's have a look at how the RBW affects the trace. Let's use a Rigol function generator to output two signals with the same amplitude and with frequencies separated by 1 kHz, and connect these two signals to the DSA-815. First, let's set the basic parameters to get the traces of the signal. We're going to set the center frequency to 5 MHz, the span to 5 kHz, and adjust the reference level to display the trace at a suitable position on the screen. As you can see, with the RBW at 3 kHz, the two signals are overlapping. Now we reduce the RBW to 300 Hz, and the analyzer can distinguish the two signals. You can also see that the frequency difference is 1 kHz. Note that the frequency difference can be conveniently measured by enabling the marker function. When you reduce the RBW, it also reduces the displayed average noise level of the analyzer. The noise is mainly thermal, which can be treated as Gaussian. The power of the noise that passes through the RBW filter depends on the bandwidth setting of the filter. The relationship between the noise level and RBW bandwidth is the delta DANL is equal to 10 log bandwidth 2 divided by bandwidth 1. Let's have a look at how the RBW influences DANL. First, we disconnect the input, then press Preset, select Sample Detector, set V to R ratio as 0.01, set the span as 50 MHz, hold the trace, enable Trace 2. Now let's reduce the RBW by 10x, and at this time we can see the DANL has reduced 10 dB. From the above demonstration, we can see that a smaller RBW can enhance the ability of distinguishing two frequencies that are near one another. It also reduces the DANL, but we should also know that reducing RBW will increase the sweep time. When the RBW is smaller than the video bandwidth, or VBW, the sweep time can be expressed by the following formula, where K is related to transient response time of the intermediate frequency filter. When we set the span to 50 MHz and the RBW to 100 kHz, the sweep time is 500 milliseconds. But when we set the RBW to 10 kHz, the sweep time will be 50 seconds. This means that when the RBW is reduced by 10 times, the sweep time will increase 100 times. This concludes our brief introduction into the resolution bandwidth of spectrum analyzers. Some key points. The RBW is the bandwidth of the intermediate frequency filter. The RBW indicates the ability of distinguishing two near-frequency signals. Narrow RBW values bring higher frequency sensitivity, and narrow RBW values will slow your sweep.